Good afternoon. Sorry for the late start again. My train, 20 minutes delayed, so I need some time to prepare. When I cleared the board, I told you last Monday I could talk to Professor Ratz, who is the responsive person for this lecture, this course. And he told me, we discussed the terms requirements. It will be much simpler than previously. So there will be one midterm exam, a test from the exercises that we do on practice, and your homework. It will be on the last week of this lecture time, before the examination period. Before Christmas, you will have a written exam. You will get one page for the midterm test, midterm exam, and the written exam, and then that will gives you a final grade, and you have to write 40% of the midterm test for the signature. That's it. That's quite simple. You will do it everything. I will upload everything what I have. You will have these slides. You have the two different type of records. So with AI or yourself, you can do everything. I uploaded the first homework just a few hours, a few minutes ago on the train. I modified because I uploaded it on the Moodle. I upload everything on YouTube and also on GitHub, and also you will find everything in Moodle. So I hope it helps. If you have any help, you can reach me. So where we are right now, we talk about some quantum mechanics, some general relativity theory, Dirac calculation, atomic structures. Why is it important? You are electrical engineers, so it's good if you know how the electron microscope, MRI, or photocell works. But the most important thing that you should understand how the conductivity works in metals and how the matter looks like. This is the second period of this talk. So, I would call the subject as solid matter, but it has a much fancier condensed matter. What we know, actually, in the work, we have perfect materials, crystals, like diamonds, or like silicon dioxide or metals. But actually this is not the case. There are more types of materials. One, crystal is simple. It's periodic in space. Sometimes it could be periodic in a plane in 2 dimensions, but in 3 dimensions it's periodic something that's crystal. If you have a liquid, and you know examples for crystal, ice, in ideal form. I mean, for example, in lake bicarb or a distilled water, or diamond or metals. You know glass. The glasses are liquids. There is a liquid, like it's viscous, like honey, or glass is a good example, or could be anything else. And you cool it quickly. Then there is no time to form these crystal structure, and you have something amorphous structure that is not amorphous. It's something not periodic. It's like liquid. Why I say this? If you go to a church, a Gothic church in Europe, and you check the glasses, during the centuries, the glass is flowing from top to the bottom. So the thickness of a medieval glass at the bottom is wider than on the top, because glass is liquid and it's flowing, just it's very slowly. Other stuff, on-off. On-off means it has no structure, or there are more structure, or there are crystals, but it's broken, so it's not crystal, not liquid. That's the on-off state of the condensed matter or solid matters. Okay, here are some examples from on-off stuff and crystals. We will go in detail in this. In a ideal world, we have ideal and perfect symmetric material. That's a crystal. That's very rare. It is sometimes desirable. Okay, it's nice. For example, in a diamond. But if you do, for example, you do something microprocessor or something like this, you also need an ideal crystal. You will understand why when I will talk about it. It's necessary. It should be as close as possible for the perfect crystal structure. The simplest stuff, you have one starting point of this crystallization. You can do very simple crystals. For example, you have a hot water. You add sugar, a lot of sugar, and then you put something in it, and then let it cool. Then you will grow crystals. Then it has one center, for example. It could be more difficult when there are many centers of this crystallization. And, well, that's another case. Micromolecular stuff, you can make crystal from proteins and DNA or viruses. It's very nice. Yeah. How it looks like, you have seen this. Well, I talked about viruses, macromolecules, and macromolecules. But the simplest stuff, the simplest case, when you have atoms in the nodes of the frame, in the crystal structure. It could be periodic, it could be a lot of things. These are just examples. However, the life is not so simple. If you just check the crystals, there could be, theoretically, 7 different crystal systems and some subsystems. The types of this primitive, I will show you examples. For this primitive, when there are particles in the nodes of the cube. That's okay. The next one, you have the cube. On the nodes, there are atoms, and there is something in the middle. Other stuff, it could be the top and the bottom of the plane of the cube. There are atoms. And could be also when there are atoms in the nodes and the center of all planes of the cube. This is how the atoms are located. I will show you examples. Okay, actually I can show you examples right now. I can go back there are two examples here. You can see the first one, the second one, or that's more difficult. Here from this primitive and body centered lattices, base centered and face centered lattices. So this is how it looks like. After learning about Schrödinger equation, you know very well this does not look like here, because there are no edges and boundaries, just possibilities, possibility functions for everything. Doesn't matter. You have this location, but and I talked about cubes. Okay, but it's not necessarily cubes. Could be cubic, tetragonal, orthonomic, triclinic, monoclinic. These are the examples and description. Triagonal, hexagonal. Sorry for the Hungarian text. I will translate it to English. I will look for another and better stuff. This is the description how the different frames look like. Okay? Examples. Okay. Nothing is perfect, even a crystal. But what defects, what errors could the crystal could have? Check here that blue one. This is just an atom which is not at the right place. Here another atom is missing. It's much more important and interesting when you have some pollution from other material. For example, very common, iron and steel. The iron could be a perfect metal, perfect crystal. Actually, it has at least 60 different crystal forms, depending on pressure and temperature and everything. Mechanical engineers learn them and write them, test and everything. But it is always polluted, for example, by carbon. Why? You know how you do the array from the minerals. You need what is it? You need, for example, carbon for the high temperature. There is always carbon. When the carbon content is something more than 2%, if I remember well, we call it iron. When the content is less than 2%, then we call it steel. But the iron is always a defect in the perfect metallic structure, crystal. There are other things like nickel and everything else, and it changed the behavior of the structure. And I will explain you how the diodes, triodes, and other transistors look like with crystals. It's also important. For example, you have a silicium crystal. Silicium has 4 electrons, more, but 4 electrons that the chemical of the electrons are 4. You put a bore. Bore has 3. That means you have a leak of charge. You also can add phosphor. I'm pretty sure not phosphor is added, but you can add it. It has 5 electrons. That's an extra. With this, you can build up transistors. And with special technology, when you don't do it with your hands, then you can do the microchips and so a few million transistors, of course. There is a special defect, Frankel defect, when there is a vacancy and an extra atom somewhere in the crystal. You have plenty of electrons. You the energy of these electrons cannot be anything, but the electron numbers could be from lower to higher. No. There is, remember this Pauli principle, at one energy level with all main principal, orbital, magnetic and spin quantum number could be only 2. It means that not all energy levels, not all electrons are on the lower level. They behave a bit weird, like a gas. It's called electron gas, and it has important here in this university for electrical engineers for conductivity and semiconductivity. But there is another. When a star dies, in a star there is thermonuclear activity in the core. When there is not enough hydrogen or helium or say silicium iron in the core, then it collapses. A small star like our sun will pump and reach a so-called red giant state and start burning hydrogen, doesn't matter, not hydrogen, helium, and but for example, a small one just use the all hydrogen and then it stops the fusion. It should be collapse. The material is very, very dense. For example, the core, the density of the hydrogen is 50 times higher than iron. So, nothing natural like an ideal gas would stop the collapse. But there is something, the electrons. The electron gas will degenerate it, doesn't matter what it does mean. And there will be something called Weindorf. Its size is like the Earth, the mass is like a star, the temperature is something 40,000 Kelvin, so it's white or blue, and that's it. In the middle, there is some degenerated electron gas. On the shell, there is something you call the normal material, and they have interesting feature. But here, you need the knowledge that these electrons will work like a gas. Yeah. The method, the electron gas, could be modeled like 3 separated electrons and also waves. I will explain you both of them and the result will be the same. Let's check the sodium. Very funny, I always call this natrium and then I recognize in English it's sodium. Let's check the natrium. The natrium has 1 chemical electron. Its mass not so big. It's quite reactive. If you take some natrium and put in water, then so something will be created and hydrogen. And this hydrogen could be, actually it's not necessary to ignite, it will burn. And also you know this natrium from the lamps, because the lamps, old lamps, use natrium in the bulb, and its color is yellow. So you know natrium. Natrium has 11 electrons, 2 on the first principal orbit, and then 8 in the second shell and 1 on the third one. Let's check now natrium. This is a single natrium atom. This electric configuration that I told you, it's like a neon is this 1 S2, 2 S2, 2 P6, it's like a neonatal. And there is one separated single electron of this natrium. There are shells where the electrons are in this atom. In the K shell, that's this 1s2. Then the next one, this L cell, is this 8. And there is one, this M cell. This happens, what I just told you, this polar exclusion principle. There are 11 electrons, and you expect to go down for the K shell, but you cannot, because cannot be all quantum numbers the same. So the principle, the orbital, the magnetic, and the spin should be different. One orbit could be only two electrons, and these electrons has a different spin. Spin is not moment and not really rotation. It's a very interesting thing. It's a symmetry. For electrons, protons, neutrons, the spin is one half. What does it mean? It means that, for example, you have this. Okay, don't consider the buttons. Half spin means you turn 180 degrees and you got the same. It's okay. You could have spin T1, then you turn it around 360 degrees and you got the same thing. The first class is the half spin called fermions. The next one with one spin called bosons. And now something interesting that we cannot imagine macroscopically. There are particles with two spins. It means that you have the particle and you have to turn around twice to get the same. 360 degrees is not enough. You have to turn around twice. That means spin 2. But it's not for electrons, protons, neutrons, but there are such particles. So you have to turn around 720 degrees to get the same. It's interesting, it's mathematics. Forgot something? Okay, so now you have one natrium atom and its energy levels in your mind. That's great. Now, step forward. You have two natrium atoms. Then could be a crystal, and you experience some split of the energy levels. It's the energy levels are the same, just these natrium atoms are moving. So the energy is a bit shifted. If you have enough particles, then these levels will form a band. Some bands are accessible, some not. This Meganegative means all of bands. There the electrons could be. When you are in a metal, you have a cloud of electrons. Slowly a cloud of electrons. We call dislocated electrons. You know this from secondary school, I guess. But it's a bit different here. These levels are accepted. Between them, there are forbidden bands. No electron could be in the valid lanes or lanes. When an electron is moving, it has certain energy level, kinetic energy, and something inside in these lanes. Its energy must be inside of these lanes. And now the important thing. If you have a crystal, then the difference between the allowed bands are huge. No electron can jump from one lane, one allowed lane to the other. It means the electron cannot move. If you give more energy or heat, then in theory the electron can jump, or some of them from one to the other, but the crystal will melt. But still, it will not conduct the current. This is the insulators. So it's isolated, it cannot move. If you have these hollow bands which are overlapped, then the electron can move. It means that the material is conductive. This is for the metals, which is very, very interesting, peculiarly interesting, is this one, these semiconductors. When there is no overlap between the allowed region, the conductive region, but the isolated layer is small, narrow. Then, from a special reason, for example, if there is a mistake, a boron or a pollution, a boron discrepancy, a boron, a phosphor, anything in the material, or you have high temperature, then the electrons can jump and can move. These called semiconductors. For example, the silicium is a semiconductor. The carbon is not a semiconductor, but the silicium is. Also the germanium is, but it's much more expensive actually, so you don't use germanium for this one. Just a remark, this is about electrons in the material, but I can tell you two other conductivity. For example, in a salted water, you have sodium and chloride ions, and those ions can get charged and can move. And also there is another conductivity, very simple. Where is it? So, I have electrons here and coming. This is also current. In the sun, for example, the material is plasma. Its conductivity is infinity, and there are thermal conductivity when the hot plasma goes to the surface. Then all charges moves. It's a current. But this is just a comment. You should understand how the conductivity works in metals, semiconductors, and how it does not work in crystals. Okay, that was the free electron model. You also can consider electrons as waves. You learned it last time. Well, at least I talk about it. It's a bit difficult to understand that everything is particle and wave. It is possible to calculate that so you have waves, you have crystals, and in the crystals there are different waves. If you have a standing wave, that's bad, because if you have a standing wave from electron, it means that the electron does not move. If it does not move, there is no current, there is no conductivity. So what is calculated here is the impulse and also the wavelength of these forbidden waves, standing waves. If you have these waves, there is no conductivity. You calculate the kinetic energy of the free electrons, the difference of the forbidden kinetic energy, and also you will get bands. If you check this very ugly, drawing, you will see dashed zones and non-dashed zones. In the dashed zones, the electron wave length or energy here are all. In the white zones, they are forbidden. These are the standing waves. This is exactly the same like we got from the free electrons. So there are gaps, there are lanes which are desirable when the electron waves can move, and there are gaps between them. This is the same like conductivity, semiconductivity. So the two models, sorry for the Hungarian text again, the two models results the same stuff. There is this insulator, isolated stuff. When there is a forbidden lane, there is so-called valence band when the electrons are moving, and the distance is big. This is not conductive. The next one is semiconductive. This forbidden lane is tight, and this one at metals, this is metals, it's written Fenek, but the pronunciation is metal, means it's, there is conductivity. Okay? Great. Now, metals. This is what I'm talking about. I will translate everything to English, sorry. It's not so easy to prepare 40 something slides. What you can see, this is one slice of a metal crystal. This big blue stuff on the corner are the ions, metallic ions, and these orange stuff are the electrons. And this is the electron gas model of metals. Just a remark, in astrophysics and astronomy, everything that is not hydrogen or helium are metal. It's more or less true, actually. Yes, all crystal, all ion are in balance. So when the attracting and pushing forces are in balance, and the ions, atoms, molecules, everything are in that place where the energy is minimum. So the crystal is a manifestation of some energy minimization. Okay, here this is natrium again, and we have one atom, and these are the energy levels. And here could the electrons are moving. If you have more, then you will have different names, and you will have the green real lane is a cloud which is moving quite freely. The metals is special because the conductivity is high. Also, they lead the heat quite well, and also they're reacting. Well, it's not the best thing in mechanics, but they're reacting quite well with the mechanical distortion for heating. It's quite special, and this is so the reason is mostly came from these free electrons. Okay. You can actually derive this stuff from The conductivity is anti-proportional to the temperature. This is very well known actually. When you switch on something, any electric stuff, then when it's cool, then the conductivity could be high, and then it kills the automatic thoughts and the secondary switch. When the temperature is higher, then the conductivity is lower. Okay, last part. That's quite interesting. The whole effect. You have very basically, you have magnetic field, and the magnetic field gives you a special current. This is what I can tell you about this. You can use the Lorentz force in magnetic field for the charged particles. These particles moving in a magnetic field. Actually, this is how it works. And finally, a special force will build it up. And if you do the calculation and everything else, then you will get a special form for the electricity, and this is the result, this one, and this gives you something. This is the particle density, elemental charge, current, magnetic field. This is the physical size of this place, and you got a special voltage. This is the whole voltage. This is given by provided by the magnetic field, and together this gives this whole coefficient, and that's it. So if you have magnetic field and you have current, then you will have a special voltage called Hall voltage. Okay, that was quick. We still have 1.5 hours, don't we? Great. So let's go back here quickly. No, it's too. That was the lecture, these field activity, whole current, and everything else. Now, switch this off. So this one.